This is a video for AQA Mechanics, Circular Motion, Section 2.1, using vectors in circular motion. Well, to show the motion of a particle moving in a plane, then we can use the vectors I and J, which are perpendicular. Quite often these will be in the northerly and easterly direction. Vectors I and J, and then we can use these to give us formulae for the following vectors. Firstly, the position vector, which is R. Notice that in print, of course, vectors are written as bold letters, although when you're writing them you would normally underline. So the position vector R, the velocity vector V, and acceleration A. If we know R as a function of time, then we can use this to analyze the motion of the particle. As an example of that, then, let's look at a particle moving in a horizontal plane, and at time t its position is given by the vector r, which is 5 cos 2t in the I direction and minus 5 sine 2t in the j direction. And we're asked to do the following things. Firstly, to prove that it is moving in a circular path centered on the origin. Then to find an expression for the velocity. Having got the velocity, we can then talk about the speed, and also get an expression for the acceleration. And once we've got the acceleration, to state the direction of the acceleration of the particle. So let's take those steps one at a time then. Firstly, starting off with proving that the particle moves in a circular path. Well, to do this we simply need to show that the modulus, or the length of the vector r, is a constant. So looking at that, we will take the square root of the components in the I direction squared, so 5 cos 2t squared, and then plus the component in the j direction, negative 5 sine 2t all squared. And that's equal to the square root of 25 cos squared 2t and plus sine squared 2t. But because cos squared plus sine squared is equal to 1, this is root of 25, which of course is equal to 5, so it's a constant, and therefore the particle is moving in a circle. And that circle is centered on the origin, and it has radius 5. The next part of the question asks us to find an expression for the velocity, and having got that, the speed at time t. The velocity is equal to the derivative dr by dt, so that's equal to negative 10, so we've got 2 coming out from the cos 2t, so it's negative a sine function, so negative 10 sine 2t in the I direction and minus 10 cosine 2t in j direction. That's our expression for the velocity at time t. The speed is just equal to the modulus of that, and so we get a factor of 10 coming out from there, but again we've got in a bracket sine squared 2t plus cos squared 2t, and therefore the speed is equal to 10. Finally, we're asked to find an expression for the acceleration. Well, the acceleration is equal to dv by dt, where we had v is equal to negative 10 sine 2t in the I direction and minus 10 cos 2t in the j direction. So differentiating again then gives us that the acceleration is going to be equal to negative 20 cosine of 2t in the I direction minus 20 sine 2t, beg your pardon, that should be plus 20 of course, so plus 20 sine 2t in the j direction. So we can see therefore that we have that the acceleration is equal to 20, and then we've got multiplied by, well, negative 20 actually I'll take out as a factor, and then that's multiplied by cosine 2t in the I direction minus sine 2t in the j direction. And this is an expression which is equal to r. So 5 times that, cosine 2t minus sine 2t is equal to r, so this is equal to negative 4r. So in other words then, the direction is in the negative r direction, so it's towards the centre of the circle. So in part E of the question, it's directed towards the centre of the circle. So we've proved then that the acceleration in circular motion is then towards the centre of the circle. This concludes this video, and then in the next one we'll be looking at motion of a conical pendulum.